like to give a short overview of acoustic noise cancellation in headphones and kind of give you a rough sense of things. I'm going to be a little bit general here, but I want to kind of give a sense of what the conversations and the questions are. And certainly acoustic noise cancellation is something that has been seen for quite a while. By the time we got to 2010, you would see acoustic noise cancellation. You saw multiple solutions in the market. You saw many different people asking questions in this space. And ever since, it's become a very, very important topic from a commercial standpoint. And so it's just kind of an interesting thing to kind of see what we're looking at there. And the simple case, and it gets modified in a lot of different sort of related topics everywhere, is the fact that at some point I wanted to be able to take in my headsets and put it, basically be near my ears. I'd like to be able to have some sort of input sound, and coming from what? Maybe from some audio files, some music I want to listen to, from some video I want to listen to, but I want to listen to the audio as well, so forth. And I'd like to be able to hear the input sound of that sound and nothing else. I'd like to have the rest of the environment disappear on me, just what I want to listen to. Very, very useful on, say, an airplane where there's noise, or there's other individuals that are creating noise, or whatever it might be. There's so many different ways and applications in this conversation. So I might want to have something where I have an input sound and I want the input sound and not any noise. Now, feels like you're dreaming a little bit because there's going to be noise that's going to be happening around it. Now, the actual mechanical structure will in fact affect that noise. Generally, it's designed to decrease the noise that goes from the outside environment into your ear, maybe 3 dB, maybe 6 dB. So, now we're talking about it in power, a factor 2 or 4. And you might think a factor 2 or 4 doesn't make a huge difference, but trust me, you hear it. A small amount makes a big difference. But it's still there. And what you're thinking is like, well, is there any way I could do something with the sound that I'm inputting here that I could somehow cancel out the noise around me? Well, that means I would need to be able to somehow sense it and then build some sort of loop around things to actually eliminate, control, move stuff around, whatever, right? So that's what I need to do next. And so you do definitely see things. So the key thing is you want the input sound, nothing else. Now, when we look at these things, we're usually assuming these are pretty small acoustically spaces, so that there's not a lot of spatial variation. Some might argue with that, but let's argue that that's not an issue here. The other thing is that this is basically going to be linear processing, at least within the earphone. So basically, I got 2 acoustic waves, and so I can actually, the waves will basically add up either constructively or deconstructively in a linear form. Okay. And so what happens then when you look at the different forms you might get, what you're going to typically say is I've got an input sound. We'll call it R of T here. And that's what I want to eventually go through the speaker, and that's what I want to see at the output. And then I'm going to have an environment, N of T. And I want it to not show up at the output. Of course, the reality is it's going to hit the overall earphone. It'll have some attenuation going through it linearly. We'll call that G1 of S. It's going to have some attenuation of that structure. And guess what? It's going to show up there unless I do something about it. Well, what can I do about it? Well, I have 2 different options. One, I can put a microphone outside and measure the environment. And then in what is called feed-forward acoustic noise cancellation, sort of know what this transfer function is of the earphone, and then sort of compute that at the right time. It's an interesting point. Immediately realizing timing here is going to be important, such that when it gets to this point, it kills everything. It kills all of the noise coming through. That would be great. Another approach is from a feedback sense, is to say, well, imagine I put a microphone inside the headset. Now, maybe the headset's kind of small, but I can still find ways to get it in there. And if I put the microphone in there, I can then build a loop to take that and say, I want to make sure that this microphone is only picking up the sound that I want and nothing else. So now I've built sort of a control loop that's now getting rid of all of the extra disturbance or noise that's coming in here through this loop. So when we talk about acoustic noise cancellation processing, it could be feed forward, it could be feedback, or it could be a hybrid, because I could actually decide to have two microphones, because if one's good, why not two? And then do the processing throughout, all the way through this loop. Now, one of the things that should immediately occur to you is that I've got this sort of noise and disturbance. It's going to have some processing. It's going to have a very short amount of delay as it goes through the structure, because again, it's just a typical transfer function. I have to make sure that anything I'm measuring shows up at the same time so it can catastrophically cancel it. If I miss, then I'm not doing a full job of cancellation. So timing matters a huge amount in these systems, and is one of the things that becomes very interesting when you start to ask questions about how to build it, what application to build it, how to put this together. But sort of in summary, this is a way to kind of think about acoustic noise cancellation and sort of the initial overall properties that you might find interesting in these spaces.